so last time we were going over an introduction to the solar system to see what we see. What does our solar system look like? What objects do we see? How do they move? How do they behave? What trends do we notice in how our solar system works? Because the goal here is to try to come up with a theory to explain why. Why does our solar system work like this? Why do we have the planets that we have? How did our solar system form? How did we get here such that we have the solar system that we have? So, quick recap from last time. What should our theory for the formation of the solar system be able to explain? Well, it should be able to explain why things move the way that they do. The prevailing motion in our solar system is counterclockwise. The sun rotates counterclockwise. All of the planets orbit the sun counterclockwise. Most of the planets rotate counterclockwise. Why? If that's a coincidence, that's a hell of a coincidence. So the fact that almost everything is moving counterclockwise suggests, there's got to be an explanation there. Hopefully our theory should be able to explain that. Not only do the planets move counterclockwise, but all of the planets are orbiting in the same plane. Sort of like this cartoon gives you the impression, right? All of the planets are moving in the same plane. It's not like some planets move like this and other planets are moving north to south or something. No, all of the planets orbit the sun in a fairly flat plane. Our theory should hopefully be able to explain that. Why are there two types of planets in our solar system? And why is it that all the terrestrial planets are near the sun and all the Jovian planets are far from the sun? Hopefully we can explain that. What about the asteroids and the comets? What are they? Where did they come from? Why are they at their locations that they're at? Hopefully our theory should be able to explain that. So 1, 2, and 3 here are most things in the solar system. And if our theory could explain the first 3, then we'd have a pretty good theory, because our theory would be able to explain how most things in the solar system work. But there are some oddballs. There are some things that work contrary to everything else. Venus and Uranus, for example, don't rotate counterclockwise. Venus rotates clockwise, Venus rotates backwards, and Uranus rotates on its side, tilted 90 degrees with respect to the ecliptic plane. So that's weird. Our moon is another oddball. Our moon is a large moon, and all of the other large moons in the solar system belong to the large planets. All of the other large moons are orbiting around Jupiter or Saturn or Neptune. The trend in our solar system is that the big moons belong to big planets. So what's our moon? What's our moon, a pretty big moon, doing around a small planet like the Earth? That's an exception to the rule. So if our theory could just explain the first 3, we'd be doing okay. But if our theory could explain the first 3 and the 4th, if our theory could explain all the major trends and the exceptions, then we'd have a better theory. Because it would be able to explain everything in the solar system and not just most stuff in the solar system. So let's see if we can't do that. All right. Well, the best theory that we have today to explain how our solar system formed is what's called the Nebular Theory. There's, as this illustration suggests, there's several steps, and we'll break this down one at a time. But the crux of the Nebular Theory is that our solar system formed from a nebula. What is a nebula? It's a cloud of gas, right? A cloud of dust and gas. So essentially, the crux of the Nebular Theory is that our solar system formed from a cloud of gas. The first step in this process is that you've got to get that gas to collapse in on itself so that it condenses, shrinks, and becomes a sun and some planets around it. So, where does that happen? Well, that happens in places like this. This might look familiar to you, maybe, because those 3 stars right there, That's Orion's belt. And so what you're looking at is this whole area is called the Great Orion Molecular Cloud Complex, where this is usually called the Orion Nebula, but there's also several other nebulae in this group of nebula. Why are all these nebula close to each other? Because this gas has been collapsing and it's been giving birth to stars. And so if we zoom in and look at the Orion Nebula, there's a bunch of stars here, right? All of these stars, most of these over here, and the ones that are still inside the gas. These are all young, newborn stars that were recently born out of the gas. Because this is how stars are born. Stars are never born one at a time. You never get a nebula collapsing and forming a star. Stars are never born one at a time. They're born in giant clusters like this, where you have huge clouds of gas. The Orion Nebula here is about 10 parsecs in radius. So what is that? That's about 50 or 60 light years in diameter. It's huge. And so when stars are born, they're born thousands at a time. And all of these new stars are all basically brothers and sisters to each other. They are all born out of the same gas. And if we zoom inside the gas, if we zoom in to look really up close at the nebula, there are still clumps of gas that are still in the process of collapsing. Right? Each of these little balls here is a lump of gas that has collapsed out of the larger nebula, and it's still going. That gravity, the mass of the gas, mass creates gravity, and so this blob of gas has enough mass that it generates enough gravity that it's pulling the gas together to, if you give this long enough, to form a star. This is a different star-forming nebula. This is called the Carina Nebula in the constellation Carina. And this is even bigger. This is just huge because you've got all of these stars over here, these stars up here, all of these stars. These are brand new shiny stars. And each of these little blobs of gas is still in the process of clumping up. The gas clumps up, and then each of those clumps collapses to form stars. So if we zoom in right here, then what you see is that out of this larger nebula, the nebula gets lumpy, and the lumps and the clumps of gas will start collapsing under gravity, and then each of those clumps forms smaller clumps. And so out of this large blob of gas, it has gotten even clumpier, and then each of these little knobs here, each of these bulbs, is still in the process of collapsing under gravity. Gravity is bringing the gas together. And given enough time, give it another 1-2 million years, each of those blobs, each of those knobs will form another star. But I'm getting ahead of myself a little bit. At the beginning, before there are any stars at all you've got is a big cloud of gas. Huge. Many parsecs in diameter. And the gas has to start out big, spread out, very low density, and cold. Really cold. We're talking 10 or 20 Kelvin. Remember what that means, right? 10 Kelvin means it is 10 degrees above absolute zero. This gas has to start out so cold that those molecules are moving so slowly that even the weak little gravitational pulls between the molecules can pull it together. That the weak gravitational attraction between these molecules can pull the gas together and start the gas collapsing because it's so cold. And so you start out with this really big nebula, and then over time it slowly but steadily starts to shrink. And then a couple other things happen. The first thing is that the momentum, the inertia of the gas causes the gas to speed up and spin faster. So remember when we talked about Newton's first law of motion, right? Newton's first law of motion is that an object in motion tends to stay in motion, right? And so the same thing holds true for rotation, that just like how an object in motion tends to stay in motion, well, an object that's spinning tends to keep on spinning under its own rotational inertia. The technical term for rotational inertia is called angular momentum. And so as this blob of gas shrinks, if that gas has any kind of spin to it at all, if that gas has any rotation at all, then it has some angular momentum. And then as gravity pulls the gas to get smaller, it spins it up faster. So that gas is getting smaller and denser and also spinning faster. And then as the gas spins up faster and faster and faster, the gas flattens out into a disk. Those blobs of gas probably start out roughly spherical, but then as it gets smaller and as the conservation of momentum, as the inertia causes it to spin faster and faster and faster, it flattens out into first off, sort of an elongated egg shape, kind of like this. And then eventually it flattens out and spins up so much that it becomes a thin disk. At the same time, you also have the energy being conserved. Because remember when we talked about energy, right? The number one law of physics is that energy has to be conserved. So when that blob of gas starts out big, it's got a lot of gravitational potential energy. It's really spread out. All that mass is far away from all the other mass, and so that blob of gas contains a lot of gravitational energy. And then as gravity causes the blob to shrink, it compresses the gas. Well, what happens to a gas when you compress it? When you compress a gas, it heats up. So that gravitational energy is being turned into heat. It's being turned into thermal energy. And the gas starts out really, really cold. But then as gravity shrinks it smaller and smaller and smaller, it gets hotter and hotter and hotter. If you let this go for about 1 million years, I said this is how stars are born. I didn't say they were born fast. So you give this about 1 million years, and that blob of gas that probably started out about a light year across. So we're not talking about the whole nebula, right? The whole nebula is many dozens of light years across. But each of those little lumps, each of those clumps and blobs of gas, the blobs of gas start out probably about a light year across. And after 1 million years, gravity has shrunk it down so that most of the mass has collapsed in toward the center. And so at the center of this blob, you have a protostar. It's not a star yet. It's a ball of gas that is still in the process of collapsing, spinning faster, heating up. It'll be a star one day, but it's not a star quite yet. It's a protostar. It's still a ball of gas in the process of getting hot enough to become a full main sequence star. All of the mass that was going too slow fell in toward the center. So all of the gas and the dust and the material from the blob, all the stuff that was going too slow fell in toward the center, and it becomes part of the protostar. All of the material that was going fast enough, all of the material that had enough angular momentum, it falls into orbit. So you've got this disk of material, this disk of gas and dust orbiting around the protostar. Why does it stay in orbit? Well, why does anything stay in orbit? Because it's going fast enough. So you have a differentiation where the slow stuff falls in and the fast stuff stays in orbit. And so you now have what's called a protoplanetary disk, where a protostar, right, a star that is basically a baby star, right? A protostar is basically a baby star. And then you have this disk of material orbiting around the protostar, and this disk is the stuff that planets and moons and asteroids and comets are born out of. All right? So this is step one. Why do we think that this is how stars and planets are born? because we can see this happening in other star-forming regions. If you look inside the Orion Nebula, sure, in the Orion Nebula there are stars that are already born, like these over here. But inside the Orion Nebula, you find a bunch of blobs of gas that are still in the process of collapsing and flattening out into disks. And also you find a bunch of protostars. All these little red spots, all these little hot spots, are protostars. They're still, they're still evolving their way into becoming fully matured stars. And then around these protostars, what do you find? A dark, thicker disk of material blocking the light from the gas behind it. Right? So the fact that we see stars forming, protostars forming, and protostars forming with these thick, dark disks around them says like, oh, well, that must be the way stars are born, right? This is, when you take pictures of baby stars, this is what baby stars look like when they're in the process of forming. And hey, if this is how these stars are born, then that's probably how our sun was born too. This is probably what our solar system looked like at the very beginning. So that's step one, right? You take that blob of gas, it collapses, it spins up into a disk, it flattens out, and it starts heating up, right? While that protostar in the center is still crunching down under gravity and still evolving its way to becoming a star, let's look at the disk here. Because once that disk starts forming, then solids start condensing out of the gas. Solid particles, solid granules start condensing out of the disk. So that's what I mean by condensation. I mean the formation of the very beginning of solids. So why am I being so vague about solids? What kind of solids am I talking about here? Well, that depends on what the disk is made of. So what is the disk made of? There it goes. A minute ago, I kept saying that the disk was made of gas and dust. Well, what do I mean by that? The gas in the disk is mostly hydrogen and helium, because hydrogen and helium are the two most abundant elements in the universe, right? Almost everything in the universe is mostly hydrogen and helium. The other gases are small molecules, things like ammonia, methane, water. So look at the periodic table here. Methane. Methane is a small molecule of carbon and hydrogen. Ammonia is nitrogen and hydrogen. Water is oxygen and hydrogen, right? So most of the gas is hydrogen and helium. The other 1.5% is small molecules of light gases. Carbon, nitrogen, oxygen, small molecules of light elements. The dust is heavier stuff. So the dust is made of things like silicon, sulfur, magnesium, calcium, titanium, iron, cobalt, the kinds of stuff that make up rock and metal. So why, right? Why is it different? Because look at these elements, right? The iron and the nickel and the calcium and silicon. These are heavier elements. These atoms have more electrons. And since they have more electrons, it's easier for them to stick to each other. So that when you have these heavy atoms floating around in the disk, they bump into each other, and when those atoms bump into each other, they glue to each other. They stick together. And they stick together and form these solid dust granules of, like 100 or 200 atoms. So we're not talking about dust like the dust in your house, right? The grains of dust in your house are huge, because the grains of dust in your house are things like, dirt that blows in from outside, or bits of hair, bits of skin, pollen grains, right? Those have billions of atoms. Those are much bigger than the grains of protoplanetary dust. The protoplanetary dust is more like particles of smoke. They're that microscopic. And so That's why we make a distinction between the gas and the dust. Right? The gas is small molecules, 2, 3, 4, 5 atoms. Small molecules made of light elements. The dust is still, it still starts out microscopic, but the dust grains are granules of 1 or 200 atoms made of heavy elements, the rocky and metallic elements. Right? So all of this gas and dust is all mixed together. All this gas and dust is mixed together. It's all orbiting around the sun, or the protostar. But it's not all the same temperature. And this is the important thing. This is the important difference. Because this is a graph of temperature versus the distance from the sun of the disk. And so the disk right by the sun got really, really hot. But then as you get further and further and further away from the sun, the disk gets cooler and cooler and cooler. The disk is made of gas and dust, but when you're looking at the disk really close to the sun, you know, it's 1,000 Kelvin, 500 Kelvin, 300 Kelvin, etc., etc. What kinds of materials can be solid at these really hot temperatures? The dust can, right? Rock and metal can be solid at these hot temperatures. Whereas all of those light elements, all those things like water and methane and ammonia, as well as some of the other gases that are in the disk like carbon dioxide, carbon monoxide, it all stays as gas because it's too hot. So no surprise then. No surprise that the planets that form near the sun are made of rock and metal. Mercury, Venus, Earth, and Mars, right? The terrestrial planets. No wonder the terrestrial planets all formed near the sun, because the only thing that can be solid when you're near the sun is rock and metal. Also, it's no wonder that the terrestrial planets are small, because look at the percentages here, right? The gas makes up 99.4% of the disk. The rock and the metal, the dust, only makes up 0.6% of the disk. So of course you can only form small planets out of rock and metal. There's not that much rock and metal to make planets out of. Right? The heavy elements, the silicon, the oxygen, the iron that makes up the Earth, as well as all those other heavy elements, like the calcium in your bones, the iron in your blood, the potassium and the phosphorus that we eat as food. That all comes from 0.5% of what the disk was originally made of. Right? That's why you get the terrestrial planets near the sun. As you get, where's my mouse? There it is. As you get farther and farther from the sun, though, the disk gets cooler and cooler and cooler until you eventually cross what's called the frost line. The frost line is the line where now you're all of a sudden far enough from the sun that the temperature of the disk drops below the freezing point. And then you can start having ice crystals. So beyond the frost line, what can condense as a solid? Well, the dust still can be solid, but also now ice. And that critical temperature, that freezing point, happens at about 150 Kelvin. There's a lot going on in this graph, and you'll see this graph some more when we talk about water in a week or two. But what is this? This is a chart that shows you whether water is a solid, ice, liquid water, or water vapor for different combinations of pressure and temperature. Well, when you're just water vapor, when you're just a water molecule floating out there in the disk, orbiting around the sun, minding your own business, there's not a lot of pressure. There's no atmospheric pressure pushing on that molecule. Therefore, the pressure is very, very low. Which means water doesn't freeze at 273 Kelvin like it does here on Earth, because here on Earth, there's 1 atmosphere of pressure pushing down on that water. Once you get to really, really low pressures, the water has to be cooled down to 150 Kelvin in order to freeze. And so in order for water to start freezing out of the disk, you've got to get far enough away from the sun, so far away that the temperature drops below 150 Kelvin. How far away is that? How far away from the sun do you have to be to cross the frost line? And that's what this equation solves for here. Don't worry, it looks uglier than it is, and I'm going to simplify it here in a second. So don't bother writing down this equation just yet. FL here is the distance to the frost line in astronomical units, and really the important thing here is how far away do you have to be to cross the frost line? It depends on the luminosity of the star. If you have a brighter star, you've got to be farther from that star to let the water freeze. So the rest of these are constants, right? The 131 is a unit conversion. The 16 and pi are just the normal numbers. The sigma there is the same Stefan-Boltzmann constant that we saw when we were looking at the luminosity equation a few weeks ago, because, I mean, basically this is a luminosity equation. And the temperature is always 150 Kelvin, right? The distance to the frost line is how far away from the star you have to be for the temperature to drop below 150 K. So if we combine all of these constants, then this simplifies to just be 3.45 times the square root of luminosity. So that's a much nicer version of this formula for you to use. And you will be using this equation for the project, so you might want to write this down in your notebook. Right? So that's step 2, right? Once you start having this disk, solids start forming out of the disk. Dust granules start forming in the inner solar system, and dust and ice crystals can start forming out of the disk in the outer solar system. The next step is that those solid particles, those dust grains and ice crystals, start to accrete. Now, what the heck does that mean? Accretion is basically a fancy word for saying gathering together. Right? Accretion is where you take a bunch of small things and you gather them together and form one big thing. So originally, when this story begins, you have just the disk has a whole bunch of little microscopic dust grains floating among the gas. But then as those dust grains bump into each other, they start sticking, basically by static electricity. Static electricity causes these dust grains to stick together, and then they run into more dust grains and get bigger and bigger and bigger and bigger. So that as time passes, and this is not a fast process, but as time passes, these dust grains bump into each other and they stick together and they form, eventually you start out with these little microscopic dust grains, and then they stick together and form bigger dust grains, and then those dust grains stick together and start forming small pebbles. And then those pebbles start sticking to each other and forming larger pebbles. And then those larger pebbles bump into each other and start forming small rocks. This is the very beginning of when rocks started showing up in the solar system, from the accretion of little dust grains gluing together to eventually form small rocks. Why do we think this is how rocks formed in our solar system? Because some of these rocks are still around. This is a piece of what's called the Allende Meteorite. This meteorite is one of the oldest rocks ever found. It formed at the very beginning of the solar system. Oh, my laundry's done. Okay. Never mind that. This rock formed at the very beginning of the solar system. It was floating around, orbiting the sun for billions and billions of years, and then at some point in the 1970s, it passed a little too close to the Earth. It got grabbed by Earth's gravity. It got pulled down to the ground, and it crashed into Mexico. It crashed into a town in Mexico called Allende, which is why it's called the Allende Meteorite. And so when you take a chunk of this rock is not very big. This is one section of the meteorite. It's about the size of your fist. And so if you cut open this rock, what is this rock made of? It's made of even smaller rocks, right? Each of these little circles here, each of these little inclusions is a small pebble, and also the really tiny ones there, the really tiny specks are dust grains. And so this rock formed from the accretion of little grains and pebbles gluing together to form bigger rocks. And then eventually, so that's when you start having rocks forming in the solar system. And then those rocks crash into each other and form bigger rocks. And then those bigger rocks crash into each other and start forming even bigger rocks, really big rocks. And then those big rocks, eventually these rocks become so big that they start having a substantial gravity of their own. And then they don't have to just randomly bump into each other. They can pull each other together by gravity. And then things start happening a lot faster, because then gravity starts pulling these rocks together, crashing them into each other. And eventually these rocks accrete together and start forming protoplanets. Right? A protoplanet is basically a baby planet, right? You start out with billions of tiny rocks, which then accrete together and form millions of big rocks, which then accrete together and form thousands of really big rocks, and then eventually accrete together and form 4 terrestrial planets. Remember, I said last time, one of the big trends in our solar system is that the smaller something is, the more of them there are. Why is that? Well, the reason why there are more small things than big things is because that's where big things come from, right? All the big things in our solar system, like planets, formed from the accretion of a large number of small things. And even today in our solar system, what do we still find? We still find lots of small things, a smaller number of medium-sized things, and a small number of big things. So this is the fact that there are lots of small things and very few big things is a big clue that says this accretion process, this is how big things formed. They formed out of large numbers of small things. And even today we have lots of small things left over. So, this is why we have 2 types of planets. Because the terrestrial planets formed near the sun where it was hot. And the only thing that could condense and accrete together to form planets were dust, was the rock and the metal. And therefore you have rocky metallic planets like Earth, the terrestrial planets. But also that's why the terrestrial planets are small, is because there wasn't that much rock and metal to make planets out of. Out past the frost line, out past about 4 or 5 AU, you've crossed the frost line. Now ice can start freezing, and there's more ice available, right? There was more ice. There's more water and methane and ammonia and carbon dioxide out there in the disk, right? There's more water available than there is dust. And so once you go out past the frost line, now you can start forming protoplanets out of dust and ice. And because there's a lot of ice, you can start forming larger, more massive protoplanets. And those protoplanets, we're talking the protoplanets that start accreting out past the frost line are 5, 10, 20 Earth masses. They are giant protoplanets of mostly ice. A lot of rock, but mostly ice. And they get to be so big that they develop a strong gravitational field of their own. And once those protoplanets get massive enough and their gravity gets strong enough, they can start accreting the gas itself out of the disk. Their gravity becomes so strong that they can just start sucking the hydrogen and the helium gas out of the disk. And all of that gas piles up onto the planet, and piling up and piling up and piling up until eventually the planets end up being mostly gas. Those are the Jovian planets. According to the Nebular Theory, this is how Jovian planets form. Jovian planets form out of a large icy protoplanet first. You have to have an icy protoplanet first. And when that protoplanet gets to be massive enough, then it can start accreting the gas, and then it it pulls in so much gas that once everything is said and done, the planet ends up being mostly atmosphere, mostly gas. It becomes a gas giant planet. In the meantime, these Jovian protoplanets are also so massive that they're able to accrete a little mini disk around themselves, so that each of these, at the very beginning, each of these Jovian protoplanets had a little disk of dust and ice and gas swirling around it. And then out of that disk, you had condensation and accretion, and that's how you get moons. That the moons of the Jovian planets accreted and formed out of the disk of dust and ice that was orbiting around the planet itself. So basically, the same process that formed the planets around the sun is what formed these moons around the planets. And also, that's why you find a lot of ice on the Jovian moons, because they formed out past the frost line where ice could freeze. And so you don't find very much ice on our moon. It's too hot here. But out there past the frost line, on the moons of the Jovian planets, you find a lot of ice frozen on those moons. And so when you start, and this is a little bit of a heads up to what we're going to talk about later on, when you start looking for water out there in the solar system, there's water on Earth, but where else is there water? Where should we be looking to find water? And maybe liquid water with some tantalizing organic molecules, right? Where should we be looking in the solar system to start finding signs of life? Hey, there's water on the Jovian moons. It's mostly frozen, but it is water. It is H2O. So keep this in mind. We'll come back to this when we start talking about moons and life in our universe. All right. So the last step is the clearing out phase, because this whole time, while the disk has been condensing and accreting and starting to form protoplanets and proto-moons, we've been ignoring the sun this whole time, right? Meanwhile, that protostar was collapsing down smaller and smaller and smaller and getting hotter and hotter and hotter. The last step is when the sun starts coming alive. Because once the sun starts heating up, not starts heating up, but once the sun heats up enough, one of the things that a protostar does right as it's about to come online, right as it's about to become a fully matured star, is its magnetic field starts to grab on to hot gas out of the disk. So you got this hot gas in the disk, right, orbiting around the star. And this hot gas gets grabbed by the magnetic field and it sprays out the north and south poles of the star as two hot jets. Why do we think this happens? Because we see this all over the sky. We see this with all kinds of protostars. Here's a bit of a movie put together by the Hubble Space Telescope of there's a protostar back there. Here's the disk orbiting around the protostar. Here's the hot gas being heated up by the star, and then you've got this hot gas grabbed onto the it's getting grabbed by the magnetic field, and it sprays out north and south, shot out of the system, shot out of the disk. What happens after that is that as that magnetic field kind of settles down, as that magnetic field relaxes, that jet, those two really fast pencil-thin jets, slow down and widen out. And instead of shooting out gas in two thin jets, the star blows out the gas in all directions. It blows out as this hot wind, and that hot wind slams into the gas of the disk, and it blows the gas out of the disk. It blows the gas out of the solar system completely. All of the light stuff that was orbiting the sun, all the gas, gets blown away by that wind, and the only thing left is all the heavy stuff. All the planets and the moons and the protoplanets, the planetesimals. I didn't say that word a minute ago, right? A planetesimal is basically a small planet, right? A planet that is still in the process of accreting to become a planet. This is the last step, right? The last step is when the sun comes online, it blows out that hot wind, it blows all the gas out of the system, and the only thing left orbiting the sun is all the heavy stuff that did accrete in the meantime. Planets, moons, etc. That's the last step. Now, the very last thing to happen is that the sun collapses down one more time, the sun shrinks down, it heats up, and as soon as the core of the sun goes over a temperature of 10 million Kelvin, then the nuclear reactions start in the core of the sun becomes a fully matured hydrogen-burning main sequence star, and you now have protoplanets orbiting around a real, honest-to-gosh star. So that's the step-by-step of the nebular theory. Right? Now, let's review. Does this theory actually accomplish the things that we wanted to accomplish? Does it explain the things that we wanted to explain? Does it explain the patterns of motion? Yeah, right? Why is it that all of the planets orbit in a thin plane? Well, because all of the planets formed out of this thin disk. Why do all of the planets move counterclockwise? Because that was the angular momentum of the blob, right? The blob started out spinning counterclockwise, and then as that blob of gas collapsed down and spun faster and flattened into a disk, everything just kept on moving counterclockwise. An object in motion tends to stay in motion. And since our blob, it doesn't have to be counterclockwise, but our blob of gas just so happened to be spinning counterclockwise, and then the conservation of momentum means that it's just going to keep on spinning counterclockwise. And then as the planets accreted and formed, they just kept on moving counterclockwise because that was their inertia. Why do we have two types of planets? Well, we have terrestrial planets because terrestrial planets, rocky planets, are the only kinds of planets you can form where the disk is too hot near the sun. Then out past the frost line, ice can freeze, and if you can have protoplanets forming out of ice and dust, then you can start having Jovian planets. What about the asteroids and the comets? Where do they come from? Well, what are asteroids and comets? Asteroids and comets are big chunks of rock and ice. Well, chunks of rock and ice are what the planets formed out of. So what are the asteroids and the comets? They're just the leftover planetesimals, right? The asteroids and the comets are bodies of rock and ice that just never did accrete. Right? They accreted together to form the asteroids and the comets, but then they never did accrete together to become part of a planet or a moon. They are just left as planetesimals. When our solar system first formed, at the very beginning, when the sun just came online, the sun became a star, there were some protoplanets, our solar system was still teeming with leftover planetesimals, with asteroids and comets, right? And accretion kept on going. Just because we had a solar system with some planets around it doesn't mean that accretion stopped, right? Accretion kept on going for about 1 billion years. When you look at all of the old surfaces in our solar system, Mars, Mercury, the Moon, all of the old surfaces in our solar system are scarred with so many impact craters from leftover planetesimals crashing into these bodies over and over and over again. For 1 billion years, rocks were raining out of the sky, crashing into everything. Every planet, every moon had enough gravity to grab onto some leftover asteroids and comets and just impact over and over and over and over again. This is what's called the period of heavy bombardment, right? For 1 billion years, the solar system was sweeping up the leftover building materials. And after 1 billion years, finally, everything that was going to get swept up basically did. And so what we see today as asteroids and comets are just the planetesimals that haven't gotten accreted yet. And in fact, accretion hasn't completely stopped. Accretion has slowed down considerably, but accretion still happens now and then, right? Every once in a while, a comet will pass by Jupiter, and Jupiter's gravity will grab it, and it'll crash into Jupiter. Or every once in a while, an asteroid passes by Earth and crashes into the Earth and kills the dinosaurs and all that, right? So accretion has slowed down a lot, but it hasn't stopped entirely. Most of the accretion, though, most of the impacts happened during that first billion years. So that's where the asteroids and the comets come from. They are the leftover building materials of the planets that just never got accreted yet. And at this point, it's been 4.5 billion years. If they were going to get accreted, they probably would have by now. You know. So that's how the nebular theory explains most stuff in the solar system. Items 1, 2, and 3. What about the exceptions? Can we use the nebular theory to also explain the oddballs? Well, we think so. Remember Venus and Uranus, right? Venus and Uranus are rotating weirdly. They're not rotating counterclockwise like everything else. You'd think, right? You'd think that, hey, conservation of angular momentum means if our solar system started spinning counterclockwise, everything should still be spinning counterclockwise. So why does Venus rotate clockwise? Why does Uranus rotate tilted 90 degrees, right? This picture here is from the Hubble Space Telescope. This is a cartoon, obviously, but this is a real picture. The sun is over here shining on Uranus, and Uranus is orbiting the sun in this plane, but it's spinning like this. Weird, weird. We think, right, the best ideas that we have today are that when Venus and Uranus first formed, they were probably spinning counterclockwise just like everything else still is. So they probably formed the same as all the other planets. And then something happened. Probably what happened is that some massive planetesimal, some huge protoplanet smashed into Venus and gave it such a punch that it reversed Venus's rotation. That there was a collision so powerful that it was able to get Venus rotating backwards. We kind of think the same thing happened with Uranus, that one or two massive collisions smashed into Uranus and knocked it on its side. So that Uranus and also the entire Uranus system, the rings, the moons, the entire Uranus system is tilted 90 degrees. Which would have been a heck of a collision, but it's possible, right? It has to happen just so, right? In order for something to collide with Venus and reverse its rotation, or collide with Uranus and knock it on its side, you gotta hit the thing at just the right angle with just the right speed. It's a heck of a coincidence, which kind of explains why it only happened to those two planets and not the rest of the planets. But the one thing we know about back then is that there were a lot of protoplanets left over, right? There were a lot of planetesimals left over during the period of heavy bombardment. We know that because there's lots and lots of impact craters, lots and lots of scars from lots and lots of impacts over a course of 1 billion years. So is it possible, is it conceivable that if you smash lots and lots of planetesimals into Venus and Uranus that you could get them to come out the way that they look right now? It's plausible. Do we know for sure that that's exactly what happened? There's no evidence to prove it. There's no evidence to say definitively, oh no, this is what must have happened to Venus or Uranus. But we know that there were a lot of planetesimals and there were a lot of collisions over the course of 1 billion years during the period of heavy bombardment. So it's plausible. It doesn't take some wild magical happenstance to cause Uranus and Venus to come out this way. It's rare. It's unlikely, but it's plausible. So that's the best idea we have today. The moon. How did such a big moon like ours form around a small planet like Earth? the best idea we have today. Actually, I shouldn't say that. There's pretty solid proof that our moon formed from another massive collision. That early on in the solar system, Earth was impacted by another protoplanet. The math says about the size of Mars. A planet the size of Mars crashed into the Earth. And here's a bit of a simulation to illustrate what I'm talking about here. Out of this collision, this massive collision threw off so much debris that, well, a lot of that debris ended up falling back down to Earth, but some of that debris went into orbit. It went into orbit around the Earth, and then it became rings. For a while there, Earth had rings of debris orbiting around it, but slowly but surely, that debris accreted together and formed one rock. And that rock was going fast enough that it stayed in orbit and it became our moon. I say we don't need to speculate because we've been to the moon, right? When the Apollo astronauts went to the moon, they brought back rock samples. And when you analyze the minerals and the rocks on the surface of the moon, it turns out that the kinds of rocks that the moon is made of are the exact kinds of rocks that are inside the Earth. Not on the Earth's surface, inside the mantle of the Earth. If the Earth and the moon formed separately, they'd be made of slightly different rocks. They'd be made of different minerals. But the fact that the moon is made of the same stuff as the inside of the Earth suggests that, well, that those rocks came from the inside of the Earth. That those rocks used to be inside the Earth, and then when that collision happened, so much material blasted off of the Earth, and then it slowly, it stayed in orbit, it accreted together, and it became the moon. So it turns out, yeah, when you've got the sheer chaos that was going on during the period of heavy bombardment, when you have billions upon billions of planetesimals left over, crashing into every planet, every moon, everything, there's a decent chance that you can have some random events where a big planet crashes into Uranus and knocks it on its side. Another big planet crashes into Earth and blasts off enough debris to create a big moon orbiting that planet. That's almost certainly, based on the rocks that we brought back from the moon, that's almost certainly how our moon formed. Is during that period of heavy bombardment, early on in the solar system, from a massive collision. Right? So, oops, there we go. Yeah, so that's why I say the nebular theory is the best idea we have today to explain the formation of our solar system, because it can explain all of the normal stuff, all the major trends, but it can also explain the exceptions. So that's why the nebular theory is the best idea, the best theory we have for explaining how our solar system formed and why our solar system looks the way that it does.